There are three ways we can use Dalton's law. So I'm going to go through each of the three problems. On your worksheet, each page is basically a different type of problem. So I suggest you sort of go in the same order that I'm going on here. Okay, so this first one says 2 flasks are connected with a stopcock. So I'm going to first draw that. So connected with a stopcock. It says that the first one has a volume of 5 liters and contains nitrogen gas. Nitrogen's diatomic, so I'm going to write the 2, and it has a pressure of 0.75 atm. It says the second one has a volume of 8 liters, contains oxygen gas, which is also diatomic, so O2, and a pressure of 1.25 atm. Okay, it says when the stopcock is opened and the gases are free to mix, what will the pressure be in the resulting mixture? So what you have to do, we have Boyle's law, right? We have volume and pressure changing. So that's P1V1 equals P2V2. It's Boyle's law that we're using along with Dalton's law. So what we have to do is figure out how much pressure will the N2 gas put on the, when it's inside the whole thing, how much pressure will that exert? And then we have to say the O2 gas, how much pressure will that exert in the whole thing? And then we can add those two pressures together. So how we're going to solve that is we're going to say P N2 V N2 is going to equal P total V total. So my pressure of my N2 is 0.75 atm. I'm going to multiply that by the volume of my N2, which is 5 liters. I don't know my pressure total, but I do know my total volume. That's the 5 liters from the nitrogen side and the 8 liters from my oxygen side gives me 13 liters total. So now I'm going to solve for P total, which is coming from my nitrogen gas. That gives me 0. And I have 1 sig fig here, so I'm just going to do 1 sig fig in my answer, 0.3 atm. I'm going to do the same thing for oxygen now. So PO2 times VO2 equals P total times V total. So again, my PO2 this time is, my pressure of O2 is 1.25 atm. My volume is 8 liters, and then my P total, I don't know, that's what I'm calculating, and then my V total, my V total is the total volume, which again is 13 liters. So I'm going to go ahead and solve that for P total of O2. And again, I have 1 sig fig because of the 8. So my answer is 0.8 atm. So now I can add these two together to get my P total final, and which is what it's asking. It's what will the pressure be from the resulting mixture? So my P total will be the 0.3 plus the 0.8, giving me 0.11. Oops, that's not what it is. 1.1 atm. Final units there. Sorry, it's not just atm. You should write atm N2 plus O2, right? Because it's the pressure of both of those gases in that volume. If it wasn't it typically is going to be the volume changing. If you were also given a temperature change here as well, you would just be using combined gas law. So that's a T1 and T2. You'd be using combined gas law instead of Boyle's gas law, and it'd be the same thing where you have to use each one to calculate P total and then add all the P totals together. So really I could give you ideal gas laws, right? I could change everything and you would still do the 1 equals the total and then you add all of the total pressures together. So the first page has questions that are like this. Another way to ask the questions, the Dalton's law question, is what you have here. So it says a 250 milliliter, this is on the second page in your 3 linked worksheets. 250 milliliter oxygen is collected over water. So over water is the key term there. So this is how it might actually take place in a lab. This is the calculation you will actually do for the lab that we're going to be doing in class. So it's collected over water at 25 degrees Celsius at a total pressure. So total pressure of 760. Then the question is, what is the pressure of the dry gas alone? So I know that my P total equals my pressure of oxygen, which is my dry gas, plus my pressure of water, right? Those are my two gases. So PT, P total equals P1 plus P2. Here my P total is, Here my P total is 760 millimeters of mercury. And then I'm looking for my dry gas, but it actually gave me the information I need to find the pressure of water. So you actually do have to look this up. It is a constant. It's on page R36. R63. It's like the green part in the back of your book that has all of the data tables. There's a water vapor pressure table like at the top of that page, R63. And so what I do is look it up by the degrees Celsius. So on that table, I'm going to find 25 degrees Celsius. And at 25 degrees Celsius, the pressure of water in millimeters of mercury is 23.8 millimeters of mercury. So that's a constant that I looked up in my book. So now in solving for partial pressure of O2, I'm going to take this 760 and I'm going to subtract the 23.8 and I get 736.2 millimeters of mercury. With proper sig figs, this doesn't count because it was a constant from the book. So my least significant place in this number is the 6. So that means I need to round to the tens place. So here's my tens place. So the 6 is going to round the 7 or the 3 up to a 4. It's not 74, it's 740 millimeters of mercury is my pressure of O2 pressure. That's the partial pressure. That's just the pressure of the dry gas. That was the term, dry gas alone, 740. So that's a second type of problem you could get. And let's see, here's the third type. This is on the third page in those 3 linked pages. This one says a gas container is fitted with a manometer. So this is how we like measure atmospheric pressure in real life, or an unknown pressure of like an unknown substance. You could use something like this. So a manometer kind of looks like this. I'm going to draw it because I think pictures help with this one and with those stopcock problems. So it kind of looks like this with like a U shape. And okay, so then it says the gas level of the mercury, so this is mercury like filled in here, is 15 millimeters lower on the open side. So I'm going to put a little line down here. And so from here to here, I have 15 millimeters. This side is 15 millimeters lower. This is my mercury all filled in here. It says using a laboratory barometer, you find that the atmospheric pressure, so that's out here, this is atmospheric pressure pushing on this side, is 750 millimeters of mercury. It says, what is the pressure of the gas in the container? So I'm just going to like label this A because it doesn't really have a gas. I mean, it doesn't really say what gas it is. So I'm trying to compare the gas outside, the pressure of the gas outside to the pressure of the gas inside. And I know that this is 750 millimeters of mercury. So this is mercury in here, and we're measuring actually the 15 millimeter difference. So if this is 750 milliliters and it's pushing harder, that means this is like 15 millimeters like weaker, if you will, which means it's 15 millimeters less than our 750. So I would take my 750, I'd subtract my 15 and get 735 millimeters of mercury equals the pressure of the gas, because we don't know what that gas was. Sig fig wise, because the 0 is insignificant, the 5 would be in the least significant place, making this here, sorry, that's kind of hard to see, this here the least significant place, which is the tens place, which means the 5 would round that 3 up to 40. So with sig figs, it would be 740 millimeters of mercury. On a test, I wouldn't have given you 750. I probably would have said 750, and if I wanted it to be 750, I would have put a point to let you know that that 0 was significant. So I would have looked for the answer of 735, but with proper sig figs, it would be 740. Okay, so those are your 3 types of Dalton's Law questions. I will do a few more for you live in class. Please let me know if you guys have any questions.